Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. Before you is a homework problem that was given. It states draw the three major resonance contributors for the molecule CNO- and rank them in decreasing contribution to the resonance hybrid. Justify your ranking fully. In order to do this, the first thing you must do is produce one Lewis structure of the molecular formula CNO-. In order to draw a proper Lewis structure, we have to determine the total number of valence electrons for CNO-. To do this, we proceed as follows. Total number of valence electrons Total number of valence electrons equals 4 for carbon, 5 for nitrogen, 6 for oxygen, and we add 1 for the negative charge. And that gives us a total of 4, 9, 15, 16 electrons. So 16 electrons. What we do next is draw the elements with their valence electrons around them. Carbon has 4. Nitrogen has 1, 2, 3, 4, 5. And oxygen has 1, 2, 3, 4, 5, 6. Now we can place 1 on the more electronegative atom. We usually should pick the more electronegative atom. More electronegative atom will hold the extra electron. That's the extra electron we get for the negative charge. So I put it on oxygen right here. Now we start joining electrons. If we do this, we see we've got 2, 4, 6, 8 around oxygen. Oxygen is happy right now. So we can begin more. We can start joining up carbon. 2, 4, 6, 7 around nitrogen. If we do another one, we've now got 2, 4, 6, 8. Nitrogen's happy, so I dump in 2 in a coordinate bond. And this will generate, we still have these 2 now for our lone pair. We'll generate this pattern, a triple bond to the carbon, nitrogen, and a single bond to the oxygen. Now I can do a quick formal charge calc. Formal charge of carbon. Carbon has 4 valence electrons from the periodic table. If I subtract what carbon has now, I've got 1, 2, 3, 4, 5. 4 minus 5 is minus 1. I have a minus 1 charge on carbon. Formal charge on nitrogen equals 5 minus 1 for each bond. 1, 2, 3, 4. 5 minus 4 equals plus 1. And formal charge on oxygen. Here we go. Formal charge on oxygen equals 6. Oxygen has 6 valence electrons from the periodic table. 2, 4, 6, and 1, 7. 6 minus 7 equals minus 1. Net charge. Net charge equals minus 1. Exactly what it should be. So it looks like we've got a minus 1, a plus 1, and a minus 1. Now I can do a quick check. First off, the charge checks out okay. I should check to make sure I have 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. And lastly, you'll note the question read, draw the 3 major resonance contributors. And the major means try to make sure you have 8 electrons around every atom. And indeed, if we check, I have 2, 4, 6, 8, 8 around carbon, 2, 4, 6, 8 around nitrogen, 2, 4, 6, 8 around oxygen. So what I'm going to do now is carry this structure over to the next page. We're going to use it as the basis for generating our next 2 resonance contributors. So I'm going to draw the structure I just had. Here it is. We had a -1 on carbon, +1 on nitrogen, and -1 on oxygen. Draw my resonance arrows. Now I'm going to apply my rules for moving electrons. And indeed, I can move electrons, according to our rules, away from a negative charge towards a positive charge. What's interesting in this case is I'm going to have to violate my own rule in the sense that I'll be moving away from a negatively charged oxygen and moving out towards a negatively charged carbon. I cannot draw it any other way because I'm trying to retain 8 electrons around each atom. If I move the pi bond out to nitrogen, away from the negatively charged carbon, I'll end up getting carbon with only 6 electrons. And so I want to try avoiding that. So initially I'm going to bring in a lone pair from oxygen, these 2 lone pair electrons, and make a new pi bond. If I do that, I'd get 2, 4, 6, 8, 10 electrons around nitrogen, and that's just not favorable. So I actually will move 2 electrons out to the carbon. And if I do this, I get a structure that looks like this. Now, if I want to check the formal charge again, I can write this down. Formal charge oxygen equals, carbon has 4 electrons, 2, 4, 5, 6. 4 minus 6 equals -2. Formal charge nitrogen equals 5 valence electrons minus 1, 2, 3, 4. 5 minus 4 equals +1. And formal charge oxygen. Oops, that first one was carbon, I'm sorry. Formal charge oxygen equals 6 valence electrons minus 2, 4, 6, 0. And my net charge now is -1. So again, if I check to have 16 valence electrons, 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 8 around every structure. So it looks like I've been successful in creating a major resonance contributor. But the charges are -2, +1, and 0. Okay, so we're going to try doing that one more time. Now, my rule for moving arrows states typically we move away from a negative charge. If I move away from the -2 charge, I will get a lone pair dumping in, recreating the triple bond. I am just going backwards to this structure. Don't want to recreate the same structure I've already created. Plus, one could also draw electrons from a neutral oxygen. If I do that, however, I'm going to create 10 electrons around nitrogen again, so I must move some electrons out to carbon. If I do this again, I'm going to get this structure. And a triple bond to oxygen with one lone pair left. So one of the lone pairs became a pi bond, and one of the pi bonds became a lone pair. I can, in this structure, check the formal charge of carbon. Carbon has 4 valence electrons, and I subtract from it 2, 4, 6, and 1 for the bond 7. 4 minus 7, wow, a -3 charge. Formal charge on nitrogen is 5 valence electrons minus 1, 2, 3, 4. We get a +1 again. Oxygen is 6 valence electrons. We subtract from it the 1 lone pair. 1, 2, 3, that makes 5. 6 minus 5 equals +1. If you add this up, my net charge is -1. So the charge is correct. 2, 4, 6, 8, 10, 12, 14, 16 electrons. 8 electrons around each. We've got a -3, a +1, and a +1. Okay, well, let us proceed now and consider how we're going to rank these structures. So I will erase my formal charge calculations. And the formal charge calculations would be present on the structures on a test. Okay. Now, the first rule we must address is rule number 4 in our rules for writing resonance structures, which simply states that structures that have filled octets around non-hydrogen atoms make greater contribution than those that don't. Now, you can take the time, and I'm going to remove these arrows just to make it easier for us to consider this. You can take the time to examine this, and you will find indeed that all of these structures have 8 electrons around every atom. So rule 4 is satisfied, but you should state this in the explanation. All structures, all resonance structures, possess filled octets. Around every atom. And that would be the first statement you'd make on a test. This allows us to move on to rule number 5a. 5a states that structures that possess less charge separation make greater contribution to the resonance hybrid. Now, let's label our structures A, B, and C, and examine what's actually going on here. Structure A has 2 -1 charges separated from a +1. The -1s are separated by a distance of one bond to an atom, even though one of the bonds is triple bond. Structure B also separates 2 negatives from a positive, although the 2 negatives are localized on one atom. So we'll address that later, but the amount of charge separation between A and B is the same. In structure C, we have greater charge separation. We have a -3 electrons separated from 2 positives, and that's greater charge separation. Because of this, we can say structure C makes the smallest contribution. Contribution to the resonance hybrid. And we can list all the reasons, and we should list them in order of priority if we can, or at least get the first one important. And that is, the biggest reason is it has greater charge separation. That's the most important reason. So it has greater charge separation, which means it than A or B, so it makes smaller contribution than A or B. But it has several other things wrong with it. Okay, and we can name those things. It possesses a very unfavorable -3 charge on one atom. This is not favorable. The next point, it has unfavorable adjacent positive charge. So adjacent positive charges are unfavorable, and it has a +1 and a +1 beside each other. And lastly, okay, the electronegative atom does not bear the negative charge. The least, and I'm going to just use capital EN, least electronegative atom. The least electronegative atom bears the negative charge. Okay. Okay, so these last three are not given in any order. The most important one is the greater charge separation. This is the real reason. Our rules are given in order of priority, but these are other unfavorable situations that are observed. The real reason is the greater charge separation. So while they all have filled octets, C produces a lot of charge separation, which makes it a minor contributor. But it also has the -3 charge on one atom, an unfavorable adjacent positive charges, and the least electronegative atom bearing the negative charge. So these are three other things, and you should list them in your answer. Now we can move on to try to distinguish between A and B. Now, in terms of A and B, we can proceed to our rules for writing resonance structures, 5B, which states that atoms bearing the negative charge that are more electronegative make greater contribution to the resonance contributor than when the negative charge is on the least electronegative atom. Now, if we compare A and B, we are shifting a negative charge from an oxygen, which is very electronegative, to a carbon, which is not as electronegative. So structure B is less favorable because it was a minor contributor. Okay. Minor compared to structure A. Why? Well, two reasons. The first, obviously, is the paramount one. Even though those two, A and B, have identical charge separation, the less electronegative atom has the negative charge in B. So less En for electronegative atom has the negative charge. I would add one more point to this. So I'll start writing at the top here. The structure B also has an unfavorable -2 charge on one atom. Now this is a minor point compared to where the negative charge is, but we should make point of it. So I'm continuing up here. So this guy, so B continues up here. So the second point, although it's less important, is note unfavorable -2 charge on one atom. This is a minor point, but it is additive. The major reason that B is a minor contributor compared to A, though, is that the electronegative atom does not bear the negative charge. Notice this observation is less important than charge separation. Again, I say the similar in charge separation because we have a plus separated from two minuses. Now, there may be a difference in this, but when we get to the next rule, 5b, the electronegative oxygen bearing the minus charge resolves that problem for us. So, now we can rank them in decreasing contribution. We start with the greatest. A makes greater contribution than B because A has the smallest amount of charge separation, has filled octets, and it has the negative charge on the more negative charge on the electronegative atom than any of the other resonance contributors. B is greater than C because it minimizes charge separation, has less concentrated charge in one atom, and it doesn't have adjacent positive charges. Right? So my ranking is given here. A is greater than B, is greater than C, and that's in decreasing order. Okay. My name's Dr. Brian Lloyd. This is my Scribblecast. Thank you very much for your time. I hope this was useful, and I'll talk to you soon.